Give a large language model unconstrained access to your local terminal, ask it to write code, and things break. Most open-source coding agents operate on a rudimentary baseline architecture. They consist of a simple Python while loop that passes a text context back and forth with a large language model. When the model decides to take an action, these standard scripts execute raw bash commands directly inside your host directory. The failure mode here is immediate. A single hallucination from the model can overwrite critical files and corrupt your active Git branch. Because the edits are live on your working directory, there is no automated mechanism for state rollback. Furthermore, when these lightweight scripts inevitably crash or hang, the local process dies. Every intermediate step of reasoning and execution context is permanently lost to a closed terminal window. Model accuracy cannot compensate for a lack of environmental control. Safe autonomous coding depends on the systems engineering that surrounds the inference loop. DeepCode, developed by the University of Hong Kong Data Intelligence Lab, approaches this by acting as an open agentic software engineering harness. It is an infrastructure layer, not an AI model itself. This infrastructure relies on a strict composition root, the DeepCodeApplication. This node completely separates the LLM from the execution engine. This kernel is agnostic to its front end, powering both a headless command line interface and the Tauri desktop workbench. To understand how DeepCode isolates and manages agent execution, we have to deconstruct 4 distinct subsystems: its memory store, its execution coordinator, its workspace sandbox, and its security gate. By treating the agent loop as a modular, multi-tier runtime, DeepCode prevents the unpredictability of an LLM from destabilizing the underlying host operating system. DeepCode discards the practice of relying purely on local script memory or a model's active context window to store session history. Instead, it relies on a relational SQLite database operating in write-ahead logging mode. This ensures transactional durability for every operation the agent performs. Every single token count, tool output, and system state change is written as an immutable domain event into the event repository. Before each new model inference, a projector reconstructs the exact conversation context directly from these SQLite tables. This is event-sourced reconstruction. If a front-end crashes or the server loses power, the session remains fully auditable. The developer can boot the desktop app back up and resume execution exactly where it stopped. Inside this durable database, agent iterations are handled by the turn service. An agent iteration in DeepCode is not a code loop, it's a managed stateful entity. Each turn transitions through a precise state machine. A turn is created as pending, moves to running, and ultimately settles as completed or failed. To prevent concurrent write races, an execution coordinator strictly caps active worker threads, issuing an application lease. This lease system drives the engine's crash recovery mechanism. The coordinator continuously monitors active worker processes for a heartbeat. If a worker process dies mid-turn, the system registers the lease as stale, exactly 15 seconds after the last heartbeat. The coordinator automatically reclaims that orphaned execution, terminates any hanging subprocesses, and safely resets the turn status. This strict coordination ensures that an agent can never enter an infinite execution loop or drain system resources unseen. Even with strict memory and process controls, allowing an autonomous agent to edit files on a developer's active working branch is an unacceptable enterprise risk. DeepCode isolates file system risk structurally through its Worktree service. Rather than touching the main directory, the harness automatically spawns an ephemeral worktree. The agent is deposited into this throwaway branch. Here, it can freely edit code, run compiler diagnostics, and execute automated tests via the terminal service. If the model suffers a hallucination or corrupts the build environment, the temporary branch is instantly discarded. No dirty state is left behind. Git worktree isolation ensures that experimental code edits remain logically separated from the production environment, allowing for verified merges rather than in-place mutation. For operations outside the worktree, DeepCode relies on the approval service. This service evaluates actions against 3 execution permission modes: auto, prompt, and read-only. When an LLM attempts to execute a shell command or a destructive file rewrite while operating in prompt mode, the system intervenes. The approval service instantly halts the active worker thread, suspending all turn execution. The application server immediately broadcasts a bidirectional JSON-RPC notification directly to the Tauri desktop UI or the CLI frontend. The entire multi-agent system sits in an indefinite wait state until the human developer reviews the exact command and clicks Approve or Reject. Moving these security gates to the protocol level guarantees that a model can never bypass human oversight through clever prompt injection. A macro view of DeepCode reveals the application route's true scale. Memory, concurrency, sandboxing, and approval layers wrap tightly around the core turn service. This includes the Model Context Protocol host, allowing external tools to plug directly into this framework. The architectural boundary is clear. The large language model is isolated. It acts merely as a probabilistic reasoning engine that generates tool requests based on compiled context. The harness is entirely responsible for formatting that context, injecting compiler diagnostics, enforcing iteration budgets, and guaranteeing system safety. Wrapping a probabilistic engine inside a deterministic application boundary creates a layer of observability and safety that raw scripts cannot provide.